All right, let's get started. Hello, everyone, and welcome to another installment of the Interstellar Probe Study webinar series. My name is James Mastandrea, and I am the Deputy Study Manager for the Interstellar Probe Study. Thank you very much for tuning in to today's webinar. We have a wonderful panel presentation today on imaging the heliospheric boundary, and after the presentation, we will have a question and answer session. Before we start, I would like to outline the logistics of today's event. As a member of the audience, your audio and video are off. During the presentations, please submit your questions in the question and answer feature, and please indicate which panelist your question is for. You may also upvote questions. During the question and answer session, I will start with questions with the largest amount of upvotes and proceed down the list. Also, for more information about the Interstellar Probe Study and for information on future webinars, please visit the Interstellar Probe Study website. And now I'd like to introduce today's speakers. Pontus Brandt is a space physicist at the Johns Hopkins University Applied Physics Laboratory with research interests in space plasma environments, especially regarding the interaction of the solar winds with planetary systems. Pontus has held many leadership positions, including being the PI of the Jovian Energetic Particles Investigation Instruments for JUICE and is the project scientist for the Interstellar Probe Study at APL. Kostas Dialynas is a research associate in the Office of Space Research and Technology at the Academy of Athens and has participated in many major international plasma physics projects. This includes being the co-I of the Shield Drive Science Center, and he is currently an active team member on the Cassini and Voyager missions. Eric Quemerais is a senior scientist at LATMOS, which is the Atmosphères, Environments, and Space Observations Laboratory in France. He has held many prestigious leadership positions and is currently the principal investigator of the SWAN SOHO detector and is the principal investigator of the Phoebus Bepi Colombo instrument. And now for the presentations. Pontus, the virtual floor is yours.
Thank you so much, James. Hi, everyone, and welcome to this webinar. I hope everybody's safe out there. So I'm just going to spend 5 quick minutes before I give the word to our distinguished speakers today. So I'm going to give you a quick background in Interstellar Probe and what it is, what we are, and the current study that we are conducting for the NASA Heliophysics Division. So this study started over 2 years ago now, and it is a trade study. It is focusing on a pragmatic mission scenario and several mission scenarios using technology that will have to be ready for launching in 2030s. The lifetime of such a mission would be 50 years, and there has to be an ability to operate far beyond where the Voyagers are today. So since we started, I've been a little bit amazed because we've seen a really incredible momentum across, not only here in the US, but across the world, as you see today with our speakers. So we have, I think, over 250 scientists and engineers from more than 9 countries that are either actively engaged or just following the study. So if you want to sign up, if you're interested, please go to our website, as I think James will show you. Next slide, please. All right, so what is this exploration about then? So we live in a bubble. We live in a magnetic bubble that we call the heliosphere. It is carved out by the solar wind that is expanding from our sun as the sun plows through the unknown interstellar medium that is built up of all the exploding stars, supernovas from around our galaxy. And of course, out there in our galaxy and around other stars, we see similar magnetic bubbles. But in terms of the environment, they are all very different from what we think our own looks like. And ironically, we're sitting inside our own habitable magnetic bubble. We know it's habitable, we're here, but we don't really know what it looks like. We have concepts of what the shape looks like, but we're sitting inside of it. It's very hard to tell what it looks like. So ever since the dawn of the space age, since the 1960s, scientists, engineers, visionaries, we've discussed leaving the sun's gravity well, go through the heliospheric boundary to really figure out what it is and go into that unexplored interstellar space. Multiple studies have been conducted in the past, but always the main technical hurdle has been propulsion to get out there quickly enough. But we think now it looks like that hurdle is actually overcome. We have the availability of large launch vehicles, such as the NASA SLS Block 2. There are other out there coming online. Next slide, please. So over these decades, the compelling science cases have not really changed. They've completely been enabled by this notion of going to a new place to make discoveries. The fundamental questions, they've always revolved around what does its bubble look like? How does this physics in the interaction region, how does it work? And also what makes it habitable? And ultimately, what lies beyond? What lies beyond the borders of our own heliosphere in the interstellar space? And certainly, not that we're going to talk about that today, but certainly for planetary science and astrophysics, that there are many unique opportunities there, including KBOs, looking at the infrared window on early galaxy formation once we're beyond our own dust clouds. But they will be talked about in future webinars, so please stay tuned for that. Next slide, please. So both speakers are going to talk about this in more detail. So I'm just going to lay out the map here to give you a sense of the enormous distances involved. I've laid out here the solar system, the heliospheric boundary, and then the interstellar neighborhood on a logarithmic scale. So the interstellar probe we are talking about is, of course, not going to Alpha Centauri that you see in this picture, but it is a mission concept going through the heliospheric boundary into the interstellar medium with the ability to operate out to about 1,000 astronomical units, where 1 AU is the distance between Earth and the Sun. So you can see it's a very large distance out there. It is a pragmatic mission concept, as I said. It would be a large strategic mission, or as we call it, a flagship class mission, that would use Jupiter gravity assist with available propulsion technologies to achieve those speeds that are more than twice than Voyager 1 today. And Voyager 1 today is the fastest escaping spacecraft from Sun's gravity well. So as such, an interstellar probe really represents the first explicit step into the galaxy for humankind. And that is really what makes this mission so unique and exciting. We put on here Voyager 1 and Voyager 2. They are the accidental interstellar explorers. I won't talk much about those at all here, but they're right now at about 150 and 124 AU from the Sun. They will likely have power only for 3 or 4 more years. They did both pass a distinct boundary that we call the heliopause, but they're still seeing these perturbations from the Sun, which means that they're still at the mere doorstep to interstellar space. From inside our bubble, missions like IBEX, Cassini, SOHO, and soon also the NASA IMAP mission and perform remote imaging of this boundary to try to figure out what it looks like and what type of physics is going on there. And completely unexpected structures have been revealed, and we're still trying to understand those. Which brings me to today's seminar or webinar. Next slide, please. So the uniqueness of an interstellar probe, of course, lies in its ability not only to image the heliospheric boundary from the changing vantage point as we move out, but foremost, once we get out, the simple notion of taking a picture of what it all looks like from outside. So Dr. Dialynas and Professor Quemerais will today talk about the most powerful imaging techniques out there. It is ENA imaging, which is targeting the hot plasma that defines the boundary of this bubble, and the UV imaging that is imaging the hydrogen flow that comes from interstellar space interacting with our bubble. So without further ado, next slide, James. Engage, and now over to Kostas and Eric, who will make our invisible heliosphere visible to you. Thanks.
Okay, so thank you very much, James, and thank you, Pontus. Next slide, please. Okay, so today I would like to shed some light to these broad questions listed here, but allow me to take a moment here to briefly explain this complex system that we call the heliosphere. So please focus on the schematic on the left for a while. Now, in a nutshell, the sun's upper atmosphere expands in the form of a magnetized fluid that we call the solar wind and travels outward with supersonic speeds. The solar material kept decreasing as the two Voyagers were moving away from the sun, but once they got close to the termination shock, where the solar wind is supposed to terminate at the front, at the shock front, all of a sudden the solar material increased, it went up. This might seem counterintuitive, but the fact is that the Voyagers had just discovered the reservoir of ions and electrons that constitute the heliosphere, which is basically the region between the termination shock and the heliopause. Now, the heliopause serves as the interface between our solar bubble and the galaxy. It is the outer boundary of our heliosphere. So the solar wind gets confined inside the heliosphere and interacts directly with a strong interstellar magnetic field. And it is this interaction that forms the heliosphere in a broad perspective, of course. Now, the interstellar probe comes from the outside, those red arrows, and meets the heliosphere in what we call the nose region, or upwind hemisphere. And then it's deflected around it. So the tail region, whenever you hear me say tail region, it's going to be the opposite direction from the nose, or downwind hemisphere. So I will try to address these questions here from the perspective of the so-called ENAs, energetic neutral atoms, that are created in the heliosphere through the charge exchange process. Once an energetic ion comes sufficiently close to a neutral atom, it steals an electron from it, and it becomes an ENA that we are able to detect with special cameras like the Inca camera on the Cassini mission and, of course, the IBEX mission. Next slide, please. So, with no further ado, this is how the heliosphere looks like in high-energy ENAs, the figure on the left in ecliptic coordinates centered at the nose. The most prominent feature in this image is this high-intensity ENA emission region, the red areas, that forms a big circle through the sky sphere. This is what we call the belt. And apart from the belt, we also identify two prominent basins, the blue areas in the figure, where the ENA intensities are much lower. They are dropped to minimum. We have now identified that these ENAs are in fact created from inside the heliosphere. The figure on the right shows how the heliosphere looks like at lower energies. It is different and includes another very unexpected feature that we call the ribbon, which is a narrow bright stripe of ENAs that sits on top of a so-called globally distributed flux. And we know now that the ribbon is created primarily from secondary charge exchange interactions beyond the heliopause. Now, what is interesting between those two figures is that the ENA emissions from the highest IBEX energy channel, which is the black outline in the left figure, correlates well with the general direction of the belt. So the takeaway point here is that we are able to see different views of the global heliosphere when looking at different ENA energies. Next slide, please. Okay, so different ENA energies, different views. But is any of these views of the heliosphere static, or is the heliosphere changing with time? And if so, what drives this change? Now, the quick answer is that the heliosphere is actually quite far from being a static structure. For example, these yearly ENA maps from Inca show that the belt intensities begin a gradual decay from the year 2003 until about the years 2012 to 2013, where the ENAs drop to minimum. And then we see a recovery in these ENA intensities. So if what I said is true, that these high energy ENAs are in fact created from ions from inside the heliosphere, then we should be able to see such changes in the ions as well. And we can verify this because we had Voyager 1 and 2 serving the heliosphere for several years before they actually crossed the heliopause. Next slide, please. And of course, I wouldn't lie to you, not intentionally at least. So it is true, and this is what we call ground truth. The in situ ion measurements from the Voyagers inside the heliosphere show a decline in the ion intensities and a recovery beginning in early of 2013, in concert with these ENA changes that we measured from Cassini. Next slide, please. But not only that, we also observe a similar situation in the lower ENA intensities from IBEX, that is a decay followed by a recovery. Next slide. So let me show you some of the details of this process. An important side note here is that there is an overlap in energies between Inca and LSCP, which provides us with a powerful diagnostic tool because we can convert these ENAs to ions and compare all measurements directly. Now, the bottom left panel shows the time profiles of high energy ENA intensities in the tail region, and the bottom right figure shows a comparison between ENAs and in situ ions towards the nose. The histories of these ENAs and ions from these opposite directions are very similar, and this was a very pleasant surprise for us. But apart from that, these changes are closely correlated with a time delay of about 2 to 3 years with the solar wind pressure changes over the solar cycle, which is the top left figure. Now, this 2 to 3 year time delay is due to the time that it takes for the solar wind to reach the termination shock. Then these ions need to charge exchange, become ENAs inside the heliosheath, and then they need to travel back to us, to Cassini and Ibex, so that we can measure them. So the inference here is that those variations in ENAs and ions are related to the solar cycle phases, as manifested in the variation of the solar wind itself. Now, details aside, these ENAs at much lower energies, which is the upper right corner, also present a similar view. Next slide, please. Okay, so when the two voyagers crossed the termination shock, they discovered that contrary to expectations, the shocked thermal plasma upstream of the termination shock remained supersonic. A substantial part of the upstream energy density went into heating the pickup ions and energetic protons. So the striking feature when we combine the energy spectra from Inca and LSCP is this change in the slope that occurs at about 40 keV, kilo electron volts, and extends to much higher energies. Perhaps this heating process that I briefly described before is translated to this change in the slope. And this is a very critical factor because this kind of normalization we can do with ENAs and ions provides an important insight on the properties of the local interstellar medium, such as the magnetic field upstream of the heliopause and, of course, the location of the heliopause itself. So the figure on the bottom informs us that the particle pressure is persistently at least 4 times and more higher than the magnetic field pressure throughout the heliosheath. And if I include the pressure from the Ibex data to this particular calculation, this fraction will become much higher. Now, all these conclusions are briefly summarized in the schematic on the right, among many other findings, of course. So the takeaway point here is that the shape of the ion and ENA energy spectra is very important to determine the pressure balance and acceleration of ions inside the heliosheath, which we need to understand in order to determine the interaction of the heliosphere with the local interstellar medium. So the upcoming IMAP mission that will extend to much higher energies than Inca, it's going to go to about 300 kilo electron volts. We'll add more points to these plots and we'll be able to explore the physics of the heliosphere in greater detail. So next slide, please. Okay, we know that both voyagers crossed the heliopause in similar distances from the sun, as is indicated in this figure, with a small offset of 2 to 3 AU. So the nose hemisphere is quite symmetric. However, the crossings from the termination shock from Voyager 1 and 2 were about 10 AU different. And if we look at the solar wind pressure about a year prior to these crossings, we will see that it was much higher in the Voyager 1 crossing. And perhaps this is the reason for this 10 AU difference. So here's the interesting fact. Back in 2002, when Voyager 1 was at about 85 AU from the sun, the measurements from LSCP on Voyager 1 showed an increase in the energetic ion densities that lasted for a few months, 6.5 months. This is what we call the near termination shock crossing that was located at a distance almost identical to the termination shock distance reported by Voyager 2 a few years later, and moreover, under similar solar wind pressure conditions. And mind you, Voyager 1 and 2 were about 130 AU apart at that time, above and below the ecliptic equator. So the dynamics of the whole heliosphere as it is determined in both ENAs and ions is certainly not a trivial problem, which of course leads me to another non-trivial problem. So next slide, please. which concern the shape and size of the whole structure. Now, the totality of all these observations together with advanced modeling can help us understand the size and shape of the heliosphere. So the heliosphere looks like a roughly symmetric bubble when looking in energetic particles. Certainly, we do not expect the heliosphere to be a perfect sphere, but for various reasons, we expect the tail to be distorted and reach to a few hundreds of AU. This view is also very consistent with the very low energy ENAs from Ibex's law, and also consistent with some models that explain the transport of galactic cosmic rays through the heliosphere. And then we have this exciting configuration from the heliosphere that we call the croissant shape, because it looks like croissant and includes two jets towards the pole, but the poles. But these jets do not merge into a single comet-type tail. Again, there are very few substantial tail-like features here as well. However, when we're looking at the intermediate energies, at Ibex high, for example, especially when considering the low energy counterpart of these ENAs, the most plausible explanation of the heliospheric configuration is a comet-type heliosphere, where the tail may extend to tens of thousands of AU. But again, looking at the traceback times of ENAs at the highest Ibex energy channel, the heliopause location may point towards a distorted bubble. So remember what I told you from the beginning, different energies of ENAs show us different views of the heliosphere. So it's a puzzle, and a very exciting puzzle if you ask me. Very low energy ENAs and very high energy ENAs together with some MHD modeling, so a rough bubble with jets, but ENAs at the intermediate energies and other modeling are consistent with a comet-type configuration. So the question is, how do we solve this puzzle? Next slide, please. Okay, so there are many ways to solve this, or at least try to solve this, and our community is already doing the effort. But I would say that the best possible method is through the Interstellar Probe mission, and here's why. So far, I'm describing our struggle to understand how the heliosphere looks like and interacts with the local interstellar medium with ENA imaging from inside the source region, so from inside the heliosphere. But once the Interstellar Probe gets outside to interstellar space, as far as 1,000 of AUs, as Pontus mentioned earlier, and looks back with its dedicated ENA imagers, it will be able to image the plasma properties and explore the actual size and shape of the heliosphere with much greater detail, especially as it moves away from it. Of course, there are other limitations in this process, and I'm not going to go into the details of that. But the point here is that the benefits of this endeavor significantly outweigh any of these limitations. This is demonstrated in the simulations at both high energies, which is the left panel, and lower energies, which is the right panel, and under different scenarios for the assumed shape of the heliosphere. Now, for all different scenarios, the innovative instruments from Interstellar Probe will be able to overcome the difficulties that I described here and provide answers to these questions, and especially when combined with the legacy of measurements from Cassini, Ibex, the two Voyagers, and of course, IMAP. It seems that in all different scenarios, the best radial trajectory for an interstellar probe to reveal the global shape of the heliosphere, which is a big target, would be through the flank regions or the poles. I think I would vote for the poles to be accurate. So having said all that, I think it's time for me to stop here and give the virtual stage to Eric Quemerais for his exciting discussion. So thank you all very much for your attention.
Thank Kostas, and now for Eric's talk.
Good afternoon, everybody. Thank you. Next slide, please. So I'm going to talk about the interplanetary background at Lyman alpha. This interplanetary background has been known for 4 decades now. It has been found out by the Argo 5 mission when 2 instruments were trying to measure hydrogen atoms in the Earth's atmosphere, and discovered that some emission was coming from outside of the Earth's atmosphere. And this emission, because of the parallax effect, has been linked to the interplanetary medium. So hydrogen atoms in the interplanetary medium can scatter solar UV photons. This emission is ubiquitous and has been used to has been studied for 4 decades, and actually it's been used by many planetary UV spectrographs to cross-calibrate the instruments by comparing the interplanetary background data. Next, please. So, what happens to hydrogen atoms in the solar system? Well, hydrogen atoms come from the local cloud in which the solar system is moving. The relative motion between the cloud and the solar system creates the wind of the interstellar wind of hydrogen atoms, which can get very close to the sun. In the solar system, the hydrogen atoms follow trajectories which are defined by solar gravitation and radiation pressure. Those effects, radiation pressure, vary with the solar cycle. And also, the hydrogen atoms can be ionized, photoionization from solar UV flux, and electron impact and ionization. But the most important effect is charge exchange with solar wind protons. Charge exchange, again, as discussed by Kostas before, is a very important source of information about the solar wind. Next slide, please. The heliospheric interface is a structure which bounds the solar system, the solar wind expansion, and is the connection between the solar wind and the interstellar medium. A very simple analogy can be made to a water flowing from a faucet into a sink. The water expands radially until it turns around and goes back to the sink. And this is about the same thing for the solar wind. Next, please. Here I'm showing a very simplified sketch of the heliospheric interface and how it is important for hydrogen atoms. So I repeat, the most important process for this study is that neutral hydrogen can charge exchange with protons, either in the interstellar medium or in the heliosphere, inside the heliosphere, and the newly created neutral will have the velocity distribution of the protons. So in the blue region, we have the very local interstellar medium. We know, we have estimated its parameters. It represents the values for the local cloud. The green region is the region where the interstellar plasma is compressed by the incoming solar system. In this region, we have a strong deceleration of the solar wind, of the interstellar plasma, and heating. When there is a charge exchange with a neutral, the new neutral has a velocity which reflects that effect. On the other side, the red region corresponds to the supersonic expansion of the solar wind. This region does not bring information for the interplanetary background because the newly created neutral has a velocity of about 400 kilometers per second, which is the solar wind velocity, and is outside of the illumination from the solar line, which has a Doppler shift of about 150 kilometers per second. However, after the termination shock, the decelerating and the heating of the solar wind into the inner heliosheath brings a third population, which corresponds to a temperature roughly of 1 order of magnitude larger than the outer heliosheath, so around 200,000 K. For this kind of study, line profiles are very important. Next, please. In terms of number density, we can present this sketch rapidly. On the left side, we have the sun. On the right side, you have in the blue marked the boundary of the local interstellar medium. And in fact, as we go between the sun to the outer heliosphere, we go through the termination shock, shown in red, and the heliopause shown in green. And between the heliopause and the boundary of the local interstellar medium, we have a pileup and accumulation of neutral hydrogen, which is due to the strong deceleration of the plasma in the outer helioschist. And that pileup has been called the hydrogen. Next, please. In terms of line shape, things are also very interesting because we can, this is a computation from a model which computes the line shape from 1 AU for an observer close to the orbit of the Earth. And you can show that the different populations have different spectral features, which a high-resolution spectrometer is able to measure. Note that for an observer moving away from the sun, the ratio between the different populations will change as the inner helioschist population will increase relative to the Earth. Next, please. The interpolatory background is a highly variable emission. It varies with, it modulates with a solar cycle. Ionization from the solar wind varies with solar cycle. Solar photons illumination also varies strongly with solar cycle. So, and there are also spatial variation, which are due to the gradient between the upwind direction and the downwind direction. Upwind being the nose direction mentioned before, and downwind being the tail direction. So, map of hydrogen interpolatory background at 1 AU show very strong anisotropies and lots of variation with the solar cycle. However, as you move away from the sun, these anisotropies decrease, but they don't disappear. We should also note that the multiple scattering effect, which is already visible at 1 AU, increases in effect. For instance, 100 AU corresponds to an optical thickness of about 10 at line center. Next, please. So here I'm going to summarize the largest data set on interplanetary background measurements obtained by the UV spectrograph on Voyager 1 and Voyager 2. So those two instruments have been observing, apart from looking at planetary emissions, they had a lot of observation of the interplanetary background. And here I'm showing a plot on the bottom right, for instance, I'm showing a plot of all the interplanetary background measurements collected by Voyager 1 between early 80s until 2011. And on the left, bottom left, Voyager 2 from same date, early 80s until 1998. As you see the gradual decrease of the background intensity. The high frequency noise is high frequency variations are linked to the change of line of sight and the anisotropies of the interplanetary background that I was talking about previously. And for instance, for Voyager 1, after 2003, we stopped the observation. We could not change the line of sight anymore, and then the intensity becomes very constant and simply falls off with distance. The top panel shows the variation of the solar illumination during the three cycles which are considered here. Next, please. So what have we learned from the UV spectrographs on Voyager 1 and Voyager 2? First, the intensity gradient is not compatible with the model without heliospheric interface. Second, because of radiative transfer, the edge wall, this pileup of hydrogen atoms in the nose direction, does not create a bump in the hydrogen map. Extension of the source emissions between the sun and the observer always wins over the increase of density. The intensity, which we can derive from those measurements, is about 0.1 AU, 0.1 cubic centimeters at about 90 AU. And also, finally, there is an excess emission in the nose region over the interface model. We will note also that there is a good agreement between the measurements of Voyager 1 and Voyager 2 at the same distance once we have corrected for the variation of the solar source. It's interesting because both Voyager 1 was over the high above the ecliptic plane, and the other one was below the ecliptic plane. But those instruments did not have any spectral information relevant for the interplanetary background. Next, please. Here I'm going to talk a bit more about this excess emissions that we observe in the outer heliosphere. So it's been estimated to about 20 Raylys. The left panel A shows the Voyager 1 UVS data as a function of time during the last part of those measurements. The B panel shows the variation of the solar flux as a function of time, and the C panel shows the ratio of those two. And what you get is a very flat result between 2004 and 2000, something like 2010, right? Which is not compatible, as I mentioned before, with a resistance transfer model of the in the interplanetary medium. So the only way to to explain this flatness of the curve is by adding an external source, which has an intensity which is similar to the interplanetary background due to the hydrogen atoms. And by combination of those two emissions, you can get something which fits the data. Next, please. What could be the source of the excess emission? Here I'm showing H alpha map of the galactic plane. Contrary to Lyman alpha, H alpha is optically thin. So you can see on very large distances. And here, the yellow regions are large emissions are linked to H2 regions along the galactic plane. And on top of that, we have overplotted scans that were performed by Voyager 2. Next, please. Yes, and what you can see is that correlated to the excess emission from from Lyman alpha, we've got also an excess, a strong intensity around H alpha. Next, please. So, if this is emission from H2 regions, although the interstellar medium is opaque at Lyman alpha line center, on the wings, photons can travel very large distances. This will lead to a two-horn line profile because the core is absorbed. We only see the wings. And the distance between those two horns will, in fact, which is about of the order of 1 angstrom, will actually depend on the column density of hydrogen between the source, the H2 region considered, and the solar system. This emission is, of course, expected to be correlated to H alpha emission. Next, please. There's another instrument who has observed the interplanetary background in the outer heliosphere, and that will continue to do so in the next few years. It's ALICE on New Horizon. And up to the orbit of Pluto, a quick comparison of the ALICE data with Voyager UVS measurements show a good agreement between the two data sets. The values at Pluto are compatible also with what we expect from the Voyager data, what we get from the Voyager data. And we look forward to new measurements in the future. Next, please. So now we've been talking about instruments that were doing measurements mainly of intensities because we didn't have enough resolution in terms of spectral resolution. So now it's time to consider having a high resolution Lyman alpha spectrograph on the Interstellar Probe. Interstellar Probe is a very interesting mission because it will allow to go, by going into the LISM, to measure directly the hydrogen number density with a spectrograph. Also, with a spectrograph with enough resolution, we can differentiate between the local emission of hydrogen and the galactic emission. So this will alleviate this kind of issues. And finally, for a spectrograph with a resolution which is high enough, like 3 kilometers per second, which corresponds to a resolution of 10 to the 5, which is HST's class of resolution, then it is possible to differentiate between the LISM population and the JHUAPL population. So of course, along the mission, it will be possible to measure and characterize each of the populations and their, as we cross the different regions outward. Next, please. And of course, what would be the best direction? So I repeat, at Lyman Alpha line center, the mean free pass of photons is about 10 AU, which means that for the core populations, like the LISM population or the JHUAPL population, we see at a distance of about 10 AU. On the other hand, in the wings, we see much farther. The mean free pass is larger than 100 AU. So in that case, for a hot population, the direction is not important. But going to the nose means that we expect to have a larger shift, Doppler shift between the H population in the nose region and the LISM. So it will make it easier to differentiate between the two. Also, in the nose region, the JHUAPL should be higher. Finally, for the external source, the direction is not very important. Well, I will finish here. Thank you very much.
All right, thank you very much to all of our panelists. And now we're going to have our question and answer session. So our first question, I'm looking at the question and answer panel. So the first one will be for Pontus, and that question is, how long would it take an interstellar probe to leave the heliosphere?
Sure, we have gotten this question many times, and there's an answer. So we've gone through upwards more than 70 staging configurations of the SLS vehicle. So using a nominal spacecraft mass, we get up to speeds up to about 8.5 AU per year. This puts you at the inner edge of the heliosphere at about 10 or 12 years, depending on that final speed. And at the outer edge, as we call the heliopause, at about less than 15 years. So this is much, much faster than Voyager 1 and Voyager 2. Voyager 1 took about 40 some years to get out there.
Thanks, Pontus. The next question will be for Kostas, and that is, does the solar circle lead to a change in the amount of solar wind, or also to the anisotropies in the direction?
Okay, so the solar cycle, of course, it leads to differences in the pressure that we get during the solar cycle. I mean, the pressure of the solar wind and the energy density leads to it's different over different solar cycles phases, as I showed in one of the plots. I don't remember which slide it was. So this is translated outwards out to the heliosheath in these ENAs and ion dropouts that I showed again in one of those slides.
Okay, thank you very much, Kostas. I think the next question might be for you as well, Kostas, and Eric, feel free to jump in as well. And that is, the HMD simulations reveal a much more complicated picture than the simple one that can be derived from the sparse, the question just moved, measurements. What is the reason for the deviation of the simple picture, and how much is that picture a result of the structure of the heliosphere / interstellar material, and how much of it is just because of the current conditions?
Okay, yeah. And can this picture change drastically in the future? Okay, I can see that. Yeah, great. So this is a good question and fair question. So basically, The MHD model that I showed, I'm assuming they're talking about the croissant shape. For example, the basic difference here, or the inclusion, was that it takes into account the solar magnetic field that apparently plays crucial role in the funneling of the solar wind into these two jet structures. And also, one of the things is that they include the pickup ions, and basically that deflates the heliosphere. But still, of course, there are differences that we need to explore. So, but these are the main two reasons for the differences between the model and the observations. And the second part of the question, let me remind myself again. Excuse me, can you remind it for me? Because
yes, that is essentially how much of this picture is a result of the structure of the heliosphere / interstellar medium.
Well, yeah. So the quick answer to that is that, in fact, once the Voyagers actually crossed the termination shock and they continued moving outwards, we found a number of surprises that we actually didn't expect. I can name a few. We didn't even expect the termination shock to be where it actually was, or the heliosheath to be so thin, or many other things. So there are many surprises that are ahead of us. So yes, these simplified, let's call them simplified, views of the heliosphere that I showed in the presentation may change somewhat in the future. And this is where the Interstellar Probe comes in. Because as I said, the Interstellar Probe will be able to look at the whole structure from the perfect vantage point, from outside. So we will be able to explore these questions in much greater detail than we already do.
Thank you very much, Kostas. And then one other question to build off your presentation is, how does the information about the magnetic field outside the heliosphere collected?
Okay, yeah, that's a very good question as well. Well, you know, a few years ago, back in in August of 2012, and then approximately 1.5 years ago, in November of 2018, the Voyager 1 and 2 crossed the heliopause. So they exited to interstellar space. And both Voyagers, these are two different missions, have magnetic field instruments, instruments that can measure the magnetic field. So this is where the information for the magnetic field upstream of the heliopause comes from these instruments on board the Voyagers.
Thank you very much, Kostas.
Thank you.
And then the next question is for Pontus. And that question is, how do you plan to select the direction towards which you will send an interstellar probe? Kostas said the poles or the flanks, yeah, you can see the question, Pontus. Yeah.
I see the question. Very good question. And the answer is alarmingly simple. We don't in this study. It is not our job to define or determine the direction. That will be the job of what we call a science definition team that will hopefully, after we get a priority in the heliophysics decadal survey, NASA will put together that definition team. And that definition team will hopefully take a look at our trade study. What we're doing here, we're looking at different directions, and we're basically listing the pros and cons and trade-offs in terms of science.
Thank you very much, Pontus. And the last question is for Eric. And that question is, Eric mentioned that hydrogen moves under action of solar gravity and radiation. What about Poynting-Robertson effect and any one of the Poynting-Robertson effects for hydrogen atoms?
The short answer is yes, it's taken into account.
Okay, thank you very much, Eric. Trying to look if there's any other questions that we can go over. Thank you very much for everyone who answered those, for everyone who asked those, and for our panelists who asked them. So I think those are all of the open questions. So yeah, so with that, that's all the time we have for today. Thank you very much to our panelists, and thank you for attending today's webinar. We are currently planning our next set of webinars, and we will communicate these upcoming webinars to you through our community listserv and our website. So please stay tuned. And to sign up for our community listserv, please visit the community involvement section of the Interstellar Probe study website. Thanks for joining us, and have a wonderful day.